For most of human history, other planets around other stars were philosophy, not science. Then we started finding them by the thousands, but we still could not see them. Not really. What we had were shadows and wobbles and mathematical ghosts. What we did not have was a picture, until now. The James Webb Space Telescope has done something that was considered nearly impossible just a decade ago. It has captured a direct image of a planet orbiting another star, and what that image is already telling us about the universe is going to take years to fully absorb. What direct imaging actually means and why it's so hard. Here is the problem nobody talks about enough when they explain why seeing an exoplanet directly is so hard. Imagine you are standing in a field at midnight and someone 1,000 miles away strikes a match. Now imagine there is also a lighthouse right next to that match. The lighthouse is not just brighter, it is billions of times brighter. And your job is to look past the lighthouse and photograph the match flame without letting the lighthouse blow out your sensor. That is the basic geometry of trying to directly image a planet around another star. The star is the lighthouse. The planet is the match. And the distance involved is so vast that from Earth, the two objects appear separated by a fraction of a single arc second, which is 1/3600th of a single degree of sky. We are talking about trying to resolve two objects that, from our vantage point, are essentially touching, where one of them is putting out roughly 10 billion times more light than the other. This is why, for the first several decades of exoplanet science, we did not actually see any of the planets we found. We inferred them. The two dominant methods were the transit method, watching a star dim slightly as a planet passed in front of it, and the radial velocity method, detecting the tiny gravitational wobble a planet induces in its host star as it orbits. Both of these methods are extraordinarily clever. Both of them are also fundamentally indirect. You are measuring the effect of the planet, not the planet itself. It is like proving a ghost exists by watching the curtains move. The first confirmed detection of a planet around a sun-like star came in 1995, when Michel Mayor and Didier Queloz announced they had found a Jupiter-sized world orbiting a star called 51 Pegasi. They did not photograph it. They measured the star swaying back and forth under the planet's gravitational pull. The planet was real, but invisible. For that discovery, they eventually won the Nobel Prize in Physics in 2019, and still nobody had seen the thing. Direct imaging, the art of actually capturing photons that bounced off or were emitted by a planet itself, requires you to solve the lighthouse problem. You need hardware that can either block the star's light precisely enough, something called a coronagraph, or separate the star and planet far enough in the image that the planet is no longer drowned out, or both. Before Webb, a handful of direct images had been captured, but almost exclusively of giant worlds 10 times the mass of Jupiter or more, orbiting so far from their stars that the separation in the sky was large enough to work with. These were not the kind of planets anyone would call Earth-like. They were behemoths in the outer dark, hot from their own formation rather than from starlight, important scientifically, but not quite what the imagination reaches for when you hear the words another planet. Webb changed the geometry of what is possible, and that is where this story really starts. The James Webb Space Telescope, what this machine actually is. Let us talk about what the James Webb Space Telescope actually is, because I think most people have a vague sense that it is big and important and replaced Hubble, and that is roughly where the mental model stops. The reality is considerably more extraordinary than that summary suggests. Webb launched on December 25th, 2021, which, for the record, is either a perfectly poetic choice or an extremely stressful way for NASA engineers to spend Christmas. The telescope carries a primary mirror 6.5 meters across, composed of 18 hexagonal gold-coated beryllium segments that folded up for launch and then deployed in space like the world's most expensive origami. It sits not in low Earth orbit like Hubble, but at a point called L2, the second Lagrange point, roughly 1.5 million kilometers from Earth, on the night side, always facing away from the sun. That position matters enormously. At L2, Earth and the sun are always in the same direction, which means Webb's enormous sun shield, a 5-layer structure the size of a tennis court made of a material called Captain, can permanently block both. That keeps the telescope cold. Deeply, profoundly cold. Webb operates at around minus 233 degrees Celsius, just 40 Kelvin above absolute zero. And that coldness is not incidental to the mission. It is the mission. Webb is an infrared telescope. It does not see visible light the way your eyes do. It sees heat radiation, the infrared glow that everything with a temperature above absolute zero emits. And this changes everything about what it can observe. Planets, even cold ones by cosmic standards, glow in infrared. Molecules in planetary atmospheres absorb and emit infrared light at specific wavelengths that act as fingerprints. Dust clouds that block optical telescopes are transparent in infrared. Webb was built to see things that are warm, things that are faint, things that are hidden behind gas, and things that are impossibly far away. Hubble is an extraordinary machine. Nobody is taking that away from it. Hubble changed cosmology. But Hubble is primarily an optical and ultraviolet telescope, and it operates in a temperature regime that makes infrared sensitivity basically impossible. Comparing Hubble and Webb is not really comparing two generations of the same instrument. It is comparing a microscope to a spectrometer. Both are tools. They are not the same tool. Webb's combination of mirror size, operating temperature, position in space, and suite of infrared instruments puts it in a category that did not exist before December 2021. It is not an upgrade. It is a different kind of eye entirely. And it was designed with one capability in mind that is central to this story: the ability to take the light from a distant object and pull it apart into its component wavelengths with enough sensitivity to read what that light passed through on its way to us. That capability is called spectroscopy, and we will come back to it, because spectroscopy is where the real news is hiding. The planet, what we're actually looking at. So what exactly are we looking at in this image? Let us profile the planet itself, because the target matters as much as the telescope. The world Webb imaged is a gas giant. It sits in a category astronomers call a directly imageable planet, which is a somewhat circular designation that means it is large enough, bright enough in infrared, and far enough from its host star that Webb's instrumentation could separate the two. It orbits at a wide distance from its star, well beyond what we would consider the habitable zone, the region where liquid water could theoretically exist on a rocky surface. Now, here's where I want to be precise, because the science press has a tendency to throw around superlatives that deserve scrutiny. This image is not the first direct image of an exoplanet ever taken. That distinction goes to 2b, a planet imaged in 2004 orbiting a brown dwarf, though the planetary classification of that object was disputed for years. And there have been other directly imaged worlds since, mostly large, hot young giants captured by ground-based telescopes using adaptive optics systems. What makes this Webb image different is not simply that it exists, it is what was done with it. Webb did not just photograph this planet the way you would photograph a streetlight from across a field. Webb stared at it long enough and with enough spectroscopic resolution to begin reading the planet's atmosphere. The image is the headline. The spectrum is the story. The planet itself is estimated to be several times the mass of Jupiter, placing it in the category of super Jovian worlds. Its temperature runs hot, several hundred degrees Kelvin, which actually aids detection since hotter objects glow more brightly in infrared. It is young by planetary standards, still radiating energy left over from its formation. Its host star is relatively nearby in cosmic terms, close enough that Webb could hold it in observation for the hours needed to accumulate the spectroscopic data the science team was actually after. The image itself, when you see it, is simultaneously humbling and quietly shocking. It is a point of light, not a dramatic sphere with clouds and storms, not a pale blue dot. A point of light, separated from the brighter smear of its host star, sitting in the darkness. And that is the thing I want you to sit with for a moment, because your instinct might be to feel underwhelmed by a dot, and that instinct is wrong. Every planet we had ever confirmed before the era of direct imaging was invisible, not dim, not hard to see, invisible in principle with any optical approach available to us. This dot represents the first category of planet where we moved from mathematical inference to actual photons. Light that left that planet traveled across light years of open space, entered a mirror built by human hands, and was recorded. That dot is not underwhelming. That dot is a first contact of a very quiet, very scientific kind. What the light is telling us, spectroscopy and the atmosphere. And now we get to the part that has the research teams genuinely electric, because the image is impressive, but the spectrum is extraordinary. Here is how atmospheric spectroscopy works, and I promise this is worth understanding because it is one of the most elegant ideas in all of science. When light passes through a gas, the molecules in that gas absorb very specific wavelengths of that light, not random wavelengths, specific ones, determined by the quantum mechanical structure of each molecule. Water vapor absorbs at certain wavelengths. Carbon dioxide absorbs at others. Methane has its own set. Ammonia has its own. Every molecule leaves its own fingerprint in the light that passes through it. So, when Webb stares at a planet and measures the infrared light coming from it, what it is receiving is a mixture. Some of that light is the planet's own thermal glow. Some of it is starlight that grazed the edge of the planet's atmosphere on its way to us. And both of those light sources have been selectively absorbed by whatever molecules exist in that atmosphere. Webb's spectrographs pull the light apart into thousands of individual wavelength channels and measure how much light is present at each one. Where there are dips in the spectrum, absorption features, those dips are signatures. Match them to the known fingerprints of specific molecules, and you can read from 1.5 million kilometers away from Earth, from light years away from the planet itself, what that alien atmosphere is made of. This is not science fiction. This technique has been used by astronomers for over a century to analyze stars. Applying it to planetary atmospheres is newer and harder, requiring the sensitivity that only Webb can currently provide for objects this far away. In the spectrum Webb captured of this planet, researchers identified absorption features consistent with water vapor, carbon monoxide, and carbon dioxide. Let me say that again, because it deserves emphasis. Water, carbon monoxide, carbon dioxide. On a planet orbiting another star, read out of the light that planet emitted and reflected, parsed by a telescope sitting in the cold dark 1.5 million kilometers from home. Now, the scientists are being careful, as they should be. These are detections at varying confidence levels. Some features are robust. Others require more observation time to confirm. Nobody is announcing that this planet has conditions friendly to life, because this planet almost certainly does not. It is a hot, massive gas giant with no solid surface we know of, in an orbit too distant, and an environment too extreme for the kind of chemistry biology requires. But that is not the point. The point is that the technique works. The point is that Webb can read an atmosphere from across the light years. The point is that the same method, refined and applied to smaller, cooler, rocky planets in habitable zones around smaller, dimmer stars is the exact pathway that leads eventually to the detection of biosignatures, molecules in a planetary atmosphere that could only be produced by living processes. Oxygen, ozone, methane in disequilibrium, the chemical signatures of a biosphere. Webb cannot do that yet for a truly Earth-like world. The rocky planets around the most favorable nearby stars are still at the edge of what even Webb can probe. But the proof of concept now exists. The pipeline is open, and the data flowing through it are already telling us something that no instrument in human history has told us before. We can read the air of another world. The history behind this moment. It is worth pausing here to understand how far we have come, because the road to this image was not a straight line, and it was not a short one. For most of recorded history, the question of whether other stars had planets was not a scientific question. It was a philosophical one. Ancient Greek thinkers proposed the idea of other worlds. Giordano Bruno was burned at the stake in 1600, partly for advocating that the stars were distant suns with their own planets. The Church found the idea theologically inconvenient. Bruno found the stake considerably more inconvenient. The scientific search for exoplanets began in earnest in the 20th century, and it was frustrating. Early claimed detections in the 1940s and 1960s turned out to be measurement errors. The instruments were not yet up to the task. The signals were too small, the noise too large, the techniques too immature. The real breakthrough came in 1992, when astronomers Alexander Wolszczan and Dale Frail confirmed planets orbiting a pulsar, the collapsed remnant of a dead star, using timing variations in the pulsar's radio pulses. These were real planets, the first confirmed ones beyond our solar system. But they orbited a stellar corpse bathed in lethal radiation, hardly the cosmic real estate anyone had in mind. 3 years later came Mayer and Queloz and 51 Pegasi b, the first planet around a sun-like star. Then the floodgates opened. The Kepler Space Telescope, launched in 2009, stared at a single patch of sky for years and found thousands of planet candidates using the transit method. By the time Kepler's mission ended, it had confirmed over 2,700 exoplanets. The number of known exoplanets today sits above 5,500 and is climbing. We went from 0 confirmed worlds beyond our solar system before 1992 to more than 5,500 in roughly 3 decades. And yet, through all of that, the images were missing. All of those worlds, every single one of those 5,500 plus planets were detected through their effects. Shadows, wobbles, timing variations. Not one of them was seen in any meaningful sense of that word until the first tentative direct images came along, mostly of those distant hot giants using ground-based adaptive optics. What Webb has now done is push direct imaging into a new regime, not just a snapshot, but a spectroscopic portrait, not just proving the planet is there, but beginning to describe what it is made of. The lineage runs from Bruno staring at the night sky and making a theological argument, through Mayer and Queloz detecting a wobble, through Kepler counting shadows, to a gold mirror in the cold dark at L2, reading the chemical composition of an atmosphere around a star we can barely name in casual conversation. That is not a straight line, but it is unmistakably a direction. What scientists are actually saying and what they're not now. I want to spend a moment on what the scientists are actually saying, because this is where the story deserves some careful handling and where the difference between a science video and a hype video really matters. The research team behind this observation has been, by most accounts, unusually measured in how they have presented the findings. There has been no press conference claiming we are close to finding life. There has been no overreach in the formal publications. What the team has said in substance, is that they successfully obtained a direct spectrum of a directly imaged planet using Webb, that the spectroscopic features detected are consistent with specific molecular species, and that the data quality represents a new benchmark for what is achievable with this kind of observation. That is it. That is the actual scientific claim. It is genuinely extraordinary on its own terms, and it does not need embellishment. What the scientists are cautious about is the jump from "we detected these molecules on this planet" to any broader conclusion about habitability, planetary formation, or atmospheric chemistry that goes beyond what the data directly support. Science is slow by design. It is peer-reviewed. It is replicated. It is picked apart by people who would love nothing more than to find a flaw in it. That process is not a bug. It is the entire mechanism by which science produces reliable knowledge rather than compelling stories. What the scientists are genuinely excited about, when you read between the lines of the careful academic language, is the demonstration effect, the fact that it worked, the fact that the atmospheric signal was as clean and readable as it was, the fact that the instrument performance matched or exceeded pre-launch predictions. Because what those things mean is that the roadmap they drew up years ago, the sequence of progressively smaller and more Earth-like targets, is not science fiction. It is a schedule, and schedules are very different from dreams. What comes next? The pipeline of discovery. So, where does this go from here? Because the image is the beginning, not the end. Webb's current target list for direct imaging and atmospheric characterization includes dozens of candidate systems. Most of them are gas giants and super Jupiters, like the world just imaged. They are the low-hanging fruit in a very tall tree, large enough and bright enough and far enough from their stars to work with the current generation of coronagraphic and spectroscopic tools. But the teams are already pushing down in size. There are rocky planets around red dwarf stars, small, dim, cool stars that are the most common type in the galaxy, that sit within Webb's potential reach for atmospheric spectroscopy under favorable conditions. The TRAPPIST-1 system, 7 Earth-sized planets orbiting a red dwarf about 40 light-years away, several of them in or near the habitable zone, has already been the subject of Webb observations. The results so far are tantalizing but inconclusive. Carbon dioxide has been tentatively detected in the atmosphere of TRAPPIST-1b. The other planets are under investigation. This is the frontier of the frontier. Beyond Webb, there is a hardware pipeline that the astronomical community has been building toward for years. The Nancy Grace Roman Space Telescope, formerly known as WFIRST, is scheduled to launch in the mid-2020s and will carry a coronagraph instrument specifically designed for direct imaging of planets around nearby stars. Roman's coronagraph is orders of magnitude more powerful than any flown before it. It is, in a real sense, the instrument that was designed to take the next step beyond what Webb is doing right now. Further down the road, and this is where it gets genuinely exciting if you are willing to think on a longer timescale, is the Habitable Worlds Observatory. This is the flagship telescope concept that emerged from the 2021 Decadal Survey, the document that sets priorities for American astronomy for an entire decade. The Habitable Worlds Observatory is specifically designed to directly image Earth-like planets in the habitable zones of nearby Sun-like stars and obtain the spectroscopic data needed to search for biosignatures. It is, in the plainest possible terms, the telescope built to answer the question. The Habitable Worlds Observatory is not funded yet. It is not built yet. It will not launch for probably 2 decades. But the fact that it is the top priority of the astronomical community and that the observational techniques it will rely on are being validated right now by Webb means the roadmap is real. We are not waiting for someone to invent the science. The science exists. We are building the hardware. And hardware, unlike hope, has a launch date. The bigger picture, why this image matters beyond science. There is a moment in 1990 when Carl Sagan asked the Voyager 1 team to turn the spacecraft's camera back toward Earth as it sailed past the orbit of Neptune, more than 6 billion kilometers from home. The image it captured showed Earth as a tiny point of light, a pale blue dot suspended in a sunbeam against the black of space. Sagan wrote about that image in a way that has not aged a single day. He pointed out that every human who had ever lived, every king and peasant, every act of creation and destruction had occurred on that mote of dust suspended in a sunbeam. And he argued that the image should force upon us a responsibility to one another and to the only home we have ever known. That image changed something, not the science, the feeling, the felt sense of what it means to be here. The image Webb just captured does something structurally similar, but in the opposite direction. Instead of turning around to see ourselves, we are turning outward and seeing somewhere else. Another planet, another world, not inferred, not calculated, seen. A point of light in the darkness around a star that is not our sun. Every philosophical and religious tradition that has ever grappled with the question of whether we are alone in the universe has done so without the ability to actually look, without the ability to point an instrument at another planet and say that one, that specific one, orbiting that specific star. Let us read its air. Let us see what it is made of. Let us find out. We now have that ability. It is crude and early and pointed at the wrong kinds of planets for the biggest question. But it exists. The capability crossed a threshold with this observation that it had not crossed before, and thresholds, once crossed, do not uncross. Think about what this means for the next generation of people who will grow up doing this science. They will not grow up in a world where exoplanet atmospheres are theoretical. They will grow up in a world where reading an alien atmosphere is something that has been done, is being done, is a career path and a telescope time allocation and a budget line item. The question will not be whether it is possible. It will be what we find. That shift in baseline assumption from it has never been done to it is being done is one of the quietest and most significant things that happens in science. And it just happened. I genuinely do not think we have let that land yet. We are moving too fast from headline to headline to stop and feel the weight of what it means that we can now see another planet and read its air. The ancient question of what is out there has always been a question we asked into a void that gave nothing back. It is still a void. It is still mostly dark and cold and indifferent, but it gave something back this time. It gave us a spectrum. It gave us water vapor and carbon dioxide and the chemical signature of an alien sky. That is not nothing. That is everything the question has been waiting for. Here is where things stand. The James Webb Space Telescope has captured a direct image of a planet orbiting another star and pulled a spectrum from its atmosphere, detecting molecular signatures that represent the first real chemical portrait of an alien world. The planet itself is not a candidate for life. Nobody is saying it is. What they are saying is that the instrument works, the technique is validated, the data are extraordinary, and the pipeline that leads from this observation towards smaller and eventually Earth-like targets is now open and operating. We are not at the moment where we find something in one of those spectra that stops everyone cold. We are not there yet. We might be decades away from that moment, or we might be closer than anyone expects, because the history of this particular search has been a story of the timeline collapsing faster than anyone predicted. We went from 0 confirmed exoplanets to 5,500 in 30 years. We went from no atmospheric detections to a confirmed spectrum of an alien world in the first 3 years of Webb's operation. Whatever comes next, it will come faster than you think. And when it does, it will build on this image, this dot of light, this point of infrared heat from a world that has never heard of us and is orbiting a star we barely have a name for, recorded by a golden mirror in the cold dark between worlds that was put there by people who refused to stop asking what is out there. We will be tracking this story as Webb continues to observe, because the next spectrum is already being taken, and we have no idea yet what it is going to say.